Drop a small steel bolt into water, and it sinks in a second. Now take that same steel, build a ship the size of a skyscraper laid on its side, load it with 100,000 tons of cargo, and it floats. More steel, more weight, and somehow it stays on the surface. Everything you assume about heavy things sinking is about to fall apart. So here are the two questions this video answers. How does something that heavy stay on top of the water at all? And once it's out there, why doesn't a wall of water in a storm simply roll it over and swallow it? By the end, you'll understand exactly what keeps it floating, what stops it from tipping over, and the hidden danger in a storm that's far worse than any single giant wave. Stand next to one of these in port, and the feeling is almost dizzying. A wall of steel taller than an apartment block, heavier than you can really imagine, resting on nothing but water. It feels like it shouldn't be allowed. Let's start with the one idea everything depends on. When you put something in water, it pushes water out of the way. The water pushes back. That upward push is called buoyancy, and it's equal to the weight of the water the object shoves aside. That's the secret hiding in plain sight. A solid bolt is tiny, so it shoves aside almost no water. The pushback is too weak to hold it up. But a ship's hull is mostly hollow space and air. It carves an enormous hole in the water, shoving aside a colossal amount, and the ocean pushes back just as hard. You can prove this at your kitchen sink. Crush a piece of foil into a tight ball, and it sinks. Flatten the same foil into a little boat, and it floats. Nothing about the metal changed. Only the shape and how much water it pushes aside. A container ship is that foil boat scaled up to the size of a town. Here's the part that flips your intuition. What matters isn't how heavy the ship is. It's how heavy it is compared to all the water it pushes away. Spread that weight across a giant hollow hull, and on average, the whole thing is lighter than water. So it floats, no matter how much steel is in it. And the scale of that is hard to picture. A fully loaded giant ship pushes aside enough seawater to fill stadiums. Every ton of cargo you add simply sinks the hull a little deeper until it has displaced one more ton of water to match. The ocean is always quietly balancing the books, but you can't just keep piling cargo on. Add too much weight and the hull sinks lower until there isn't enough hollow left to push back. That's why every ship carries a painted mark on its side, a line that shows how deep it's allowed to sit. It came from a 19th century reformer who was tired of overloaded ships vanishing at sea. So floating is solved, but staying upright is a completely different problem. A tower of containers stacked 5 stories above the deck looks like it should topple at the first big lean. It doesn't. And the reason is one of the most elegant tricks in engineering. Every ship has 2 competing points. One is where its weight pulls down. The other is the center of the underwater shape, where the push comes up. In calm water, they line up, and the ship sits level. Now watch what happens when a wave tips it. As the ship leans, more of one side dips underwater. The underwater shape changes, and the upward push shifts toward the low side. That off-center push acts like a lever, rotating the ship back upright. The harder a wave shoves it over, the harder the water shoves it back. Engineers have a name for the point this balancing act depends on. As long as it sits above the ship's center of weight, every roll creates a force pulling the ship back to level. Push it too far, though, past a critical angle, and that same force flips into a push the other way. Beyond that line, the ocean stops saving the ship and starts rolling it on. There's a catch. This self-righting only works if the weight is kept low enough. Pile too much high up, and the ship becomes top-heavy and unstable. So crews flood tanks deep in the hull with seawater and load the heaviest cargo near the bottom, keeping the ship's weight pinned low so the ocean can always win the fight to right it. It's a constant balancing act. Too top-heavy and it rolls dangerously. Too bottom-heavy and it snaps upright so hard it can damage cargo and crew. Good seamanship lives in that narrow middle between tipping over and being thrown around. So now the ship floats, and it rights itself. You'd think a storm is just about surviving the biggest possible wave, but the deadliest threat in heavy seas isn't the size of a single wave at all. It's something far quieter, and it can build out of nowhere. Sometimes, in seas that look almost ordinary. Here's the twist almost nobody outside the industry knows. A ship has a natural rhythm, a speed at which it likes to roll side to side. If the waves start hitting in time with that rhythm, each wave adds a little more to the roll. exactly like pushing a child on a swing. Small, perfectly timed pushes can grow into a violent, dangerous swing. It gets stranger. In certain waves, the ship's own stability flickers. As a big crest passes beneath the hull, the shape touching the water briefly shrinks, and for a moment, its ability to right itself drops. Time that wrong, again and again, and a ship can suddenly snap into wild rolls in seas that didn't even look that threatening. This is not a rare curiosity. Rolls like these have ripped stacks of containers off ships' decks and dumped them into the ocean, sometimes hundreds at a time. Cargo worth fortunes, gone in minutes. Not from a monster wave, but from a rhythm the crew couldn't see coming. And this reaches your life directly. Almost everything around you, your phone, your clothes, the parts in your car, crossed an ocean stacked on a deck like that. The entire modern world floats on the fact that these ships almost always stay upright. Almost. So captains fight it by changing course or speed, breaking the deadly timing before it builds. And the hull itself has another surprise. A ship this long doesn't stay perfectly rigid in big waves. It bends, flexing along its length as crests pass underneath. If it were stiff, it would crack. It survives the sea by bending with it, not against it. So here's the full answer. A ship floats because its hollow shape shoves aside more water than its weight, and the ocean pushes straight back. It stays upright because every lean shifts that push into a lever that rights it. And it survives storms by keeping its weight low, dodging dangerous rhythms, and bending instead of breaking. A ship never beats the ocean by being heavier or stronger. It survives by working with the water, floating on what it pushes aside, leaning on the sea to stand back up, and flexing through the waves it can't fight. It stays on top not by force, but by agreement with the water beneath it. If you want the next video to break down another hidden system running quietly behind your everyday life, subscribe.